So our first type of type 3 reactions with carbonyls is going to concern halogenation. Right? It seems like halogenation is always very important. And the reason is because if we can put a halogen on these molecules, then we can maybe turn around and get those halogens to come back off as leaving groups and replace them with something else that's a little bit better, or maybe something that we would want in the first place. So we need to take a look at halogenation reactions with carbonyl groups. So when Br2, Cl2, or I2 is added, right? Those are really three halogens that we've always kind of traditionally seen in every lecture when it concerns halogen, to a aldehyde or ketone. Okay, so I'm going to put in here big bold letters, aldehyde or ketone, type 2s, right? What we can see is that the halogen replaces one or more of the alpha hydrogens of the carbonyl compound. The reaction has to be catalyzed, which means we have to throw a catalyst in to get this thing to happen. And this catalyst could be an acid or a base. So next step, we need a catalyst. And this catalyst could be an acid or it could be a base. Depending on what we use, that will kind of tell us whether one or multiple halogens go onto the molecule. This is called an alpha substitution reaction. So a new term that we can bring into the picture, alpha substitution. And the reason is because you're substituting a halogen for a hydrogen that was on the molecule. So let's just look at the overall reaction first, and then we'll look at the mechanism that goes on. So here's a ketone, and we are reacting this with Br2 in some acid. So what happens is that our carbonyl stays intact. Why? Mechanism will tell us. Our Br attacks the molecule, and it attacks the alpha hydrogen of a molecule. Now, where is the alpha hydrogens? The alpha hydrogens are on the alpha carbons. So an alpha carbon could be here, and an alpha carbon could be there. So it's really symmetrical. It's your choice on which one you want to pick. I'm just going to pick the one over to the right-hand side, and what we see is that a new group comes on, it kicks the hydrogen off, and one of the bromines go on in that location. So that's the acid-catalyzed halogenation of an aldehyde or ketone. Okay, well, let's take a look at another example. Let's say that we've got a carbonyl, and on this side, let's say that we've got a benzene ring, and on this side, let's just say that we have an ethyl group. And let's just add chlorine this time instead of bromine, just to make it a little different. And we want to know what happens here. Well, we don't need the mechanism just yet. We'll look at that in a minute. But if I look at this molecule and I try to figure out what goes on, this carbon has an alpha carbon that's here to the left, and it has an alpha carbon that's here to the right. Well, if I look at the one to the left, this is different than the one on the right. So maybe at first glance you would think that we would get a different product or a mixture of different products, and maybe so, but in this case we don't. And the reason is because the carbons have to have alpha hydrogens in order to be kicked off and substituted. So this carbon to the left, it doesn't have any alpha hydrogens. There's no alpha hydrogen there on that molecule. And because it doesn't have an alpha hydrogen, well, it doesn't have a spot for the incoming halogen to be attached to. So this one is off guards. We can't do a reaction on that side. Sorry, try again. So this benzene is actually going to stay untouched. And the ethyl group on this side, well, that does have an alpha hydrogen. So that alpha hydrogen is going to be kicked off and replaced with an incoming halogen. And our chlorine goes there in the alpha carbon spot. So that's the acid-catalyzed halogenation of an aldehyde or a ketone. We did ketone examples here, but aldehydes are very similar. Okay, well, how is that different than a base-catalyzed reaction? Okay, so let's scroll on down and let's do an example of a base. So let's say for a minute that we have a carbon double bond O, and on this side, let's say that we've got a CH2CH3, and on this side, let's do a benzene ring. So the same molecule from up above. And let's add the same halogen from up above, a Cl2. Right? Okay, so what I've done is that I've changed the skeletal structure here into a CH2CH3 just so we get to see this a little bit better. That's all that I've done. And instead of a acid, let's use a base, OH minus. This mechanism is a little different. And this mechanism will force a different type of product. Well, the halogen still targets the alpha carbon as long as it has alpha hydrogens on it. And what happens here is that the halogen targets the alpha carbon, and it just doesn't replace one hydrogen, it replaces every single alpha hydrogen that we have available. So that means in the product here, well, I'll take my benzene ring. I know that that does not have any alpha hydrogens at all because that carbon doesn't have any hydrogen, right? It's already incorporated into 4 bonds, doesn't have a hydrogen. On this side of the molecule, however, we have CH2 and CH3. Under a base-catalyzed reaction, what happens is that we first substitute one of the hydrogens with the halogen. So Cl goes on in the first round. Under basic conditions, however, this is allowed to happen again. So we can erase this other alpha hydrogen that's there, and another chlorine can go on in its spot. So we get a double dip here, right? Who said double dipping was bad? In this case, it might be okay, and we form what we call a geminal dihalide, right? Gemini, gem, same carbon. Dihalide, halogens on the same carbon. So this is the difference between an acid-catalyzed and a base-catalyzed reaction mechanism as far as halogenation goes. So the thing that you have to remember here is that under acidic conditions, the halogen will substitute for only, and I'm going to put a star here, one of the alpha hydrogens. Under basic conditions, however, the halogen substitutes for all of the alpha hydrogens. So we will see why this happens in the next video when we look at the mechanisms and talk about the purpose of the acid. Why is acid required for this reaction to go forward? And why is the hydroxide required for the reaction to go forward? What are they really doing? What's going on with the acid and the base parts of these reactions? So that is what we will focus on in the upcoming video. So please stay tuned. We're going to get a curvy arrow mechanism for both of these, and you're going to kind of see there's not really any kind of surprising steps that we are introducing. Now that you've seen so many of these mechanisms, really, it's going to be the same story over and over and over.